Hello, everyone. My name is Yash Sharma. I'm a PhD student at the Max Planck Research School for Intelligent Systems, and I'm honored to be invited to give a keynote presentation at this workshop. While I have little to no experience with medical applications, I have done some work on disentanglement, which I hope will be useful for the audience. As a side note, I'm sorry that I couldn't be there at the workshop. I'll be going fairly quickly in the interest of time. But I've asked the organizer to share my contact information with the audience, and so if you do have a question, please feel free to send me a message. What I'd like to speak with you about are the progress in representation learning that we're currently seeing, and better understanding that using mathematical formalisms as a way in which that we can kind of, in a principled manner, derive and make predictions about what would be the next steps that would be great for representation learning. And that's hopefully what I can get across with you today. So what definition are we using for representation learning? As with any deep learning or machine learning concept, I'm sure many people have many different definitions. So the definition that I'll be using is the goal of representation learning is to learn representations of the data that facilitate the extraction of useful information for solving downstream tasks. In short, if we look at the figure on the left, extracting a representation or using a function to map our input to some kind of output, ideally a lower dimensional output, that is very useful for a variety of downstream tasks. And there have been a number of benchmarks that have sort of looked at different training algorithms, pre-trained on different training data sets, and then measured on different end tasks or downstream tasks, like image classification or semantic segmentation. So by recent progress, what I mean is really the advancements in, say, self-supervised learning, which allowed for training at very large amount of scale, and have been shown to provide very useful performance for a variety of downstream tasks. And here I only have two examples, but one can kind of look at the success of GPT-3 and BERT and kind of this propagation of this sort of idea foundation models being useful for a variety of downstream tasks in a transfer learning sort of way, as all instantiations of the same kind of phenomenon. So in the figures that we have here on the slide, what we can see is a comparison between self-supervised learning, which train learning representations without leveraging labeled data, and thereby holding some kind of promise that you're not biased towards a particular downstream task, but you're hopefully universal across many different downstream tasks. And comparing to supervised learning on a particular downstream task, which is likely going to be biased for that downstream task and could possibly discard information that may be useful for a number of downstream tasks. And we've seen with like one of the recent self-supervised learning algorithms like MICCAI outperforming image and unsupervised pre-training across a variety of downstream tasks. We've also seen in the medical space where self-supervised learning has outperformed supervised pre-training in terms of transferring to label expensive medical image classification benchmarks, such as, I guess, chest x-rays, I believe the downstream task would be here. But these are all instantiations of a similar kind of idea that self-supervised learning at scale, especially when you don't have enough label data, can be very beneficial for learning a good representation that's useful for a variety of downstream tasks. And if we look at different self-supervised learning algorithms, they all share similarities, but also dissimilarities. And I think when we were going about an analysis, and we want to have an analysis which is really characterizing the fundamentals and the core of what's going on, we want to understand really what's similar between all these methods that work, apart from the fact that we're training with a large amount of scale, of course. So if we look at many different methods that have been successful in the literature and like hone in on, say, SimClear, which is, I would say, the simplest kind of framework for contrastive learning, that's kind of in the name. And we have like a representation of what the SimClear process is on the right. We're maximizing similarity between different views of the same image while maximizing dissimilarity between different views of different images. And the idea here is we're going to use augmentations to get different views of the same images. And these augmentations should be variable enough that we're able to discard lots of nuisance factors that don't really matter for the downstream task of interest. So for example, if we care significantly about object classification, we can see with this dog image, these two different views are very different. They're color distorted, they're different crops. But I think if we were to assign a class label to both these images, we would both say that these have characteristics of a dog. And so if we can take these highly different sort of views and map it to the same place in latent space, we're basically asking for an invariance. We want to be invariant with respect to, we want to recover the information that is invariant with respect to the augmentation while discarding the information that is variant with respect to the augmentation. But of course, if we were to just say maximize similarity, there are trivial solutions, shortcut solutions. It's objective. You could map every image to a constant vector, and then you have maximum similarity, but you haven't learned anything meaningful that differentiates images from each other. And so this dissimilarity, this contrastive learning, this moving different images away from each other is one way to avoid collapse, and many different methods have different other ways to avoid collapse. But what we're going to focus on here is that aspect of learn augmentations of a given image and then maximize similarity between views. And if we want to mathematically instantiate that, we number one need to define a transformation distribution. This is because we typically stochastically sample augmentations. We can crop in many different ways for a same image. We can color distort in many different ways for the same image. And so we define some kind of stochastic distribution for transformations. We sample said transformations to give rise to your views. And then we propagate said views through an encoder to give rise to the representation, which is kind of the goal of representation learning. And we want this representation to be good. And typically benchmark whether this representation is good by learning many different task predictors, trying to map this representation to, say, a semantic segmentation output, or say to an image classification output. And we want it to be useful for all these variety of downstream tasks. The one aspect of this slide, which I guess is new information that we maybe should talk about, is for the analysis I'll be presenting, which me and my collaborators have worked on in this presentation, we honed in on SimClear and contrastive learning in particular, which uses kind of particular objective function influencee. Like the mathematics here might be hard to kind of digest if on first seeing this sort of equation. But at the end of the day, what we're doing here is we're sort of saying we want to maximize similarity between different views of the same image, which is represented by the same index, and minimize similarity between different views of different images, which is represented by the different indices. And that's all this objective is really doing at the end of the day. And I guess let's take a step back and sort of and think about how can we develop a framework for analyzing representation learning. So of course, empirical works have sort of looked at different downstream tasks and tried to see, try to benchmark representation learning by seeing if you have a suite of downstream tasks. I know there's like a visual task adaptation benchmark, which may fit that bill. We want a representation which is useful for all of these downstream tasks. But then again, like what are the characteristics of this representation? We're not really giving a mechanistic interpretation of what's going on. We're instead just saying, we have a representation, we don't really know what's in it, but it's very useful for a bunch of downstream tasks. But what would be that representation that would be useful for a bunch of downstream tasks? And for that, we need to sort of take a latent variable model perspective, where there are certain latent variables, some lower dimensional description for images or high dimensional observations, which can be mapped to said observations, does uniquely distinguish one image from all of the other images, but is significantly lower dimensional than the original high dimensional observation. And we can see examples for that below. Here we have a D-sprites image, and these images can be extremely large. They can be 64 by 64 or 256 by 256 or 1024 by 1024. But the data set is so simple that each image, regardless of the dimensionality of the pixel space, regardless of how many pixels we have, can be described with 5 variables. The only factors of variation are shape, X and Y position, scale, and rotation. And every single one of these images, if we know the shape, the position, the scale, and the orientation, you can distinguish a single image from all of the other images. And what this means is that if our representation learning algorithm, if our deep neural network extracts that 5-dimensional representation from this arbitrarily high-dimensional observation, that representation is extremely low dimensional, and it's perfect for any downstream task because any downstream task can be a function of said variables. And to give an example as to how this kind of matters in the real world, if we took a look at, say, those dog images or that couch image from before, there would be different aspects of this image that we would also kind of correspond to factors of variation. Irregardless, we would not be talking about the pixels in the dog image or the pixels in the couch image. It would be these kinds of semantics that we describe the image with, and that can be described in a significantly lower dimensional way. So extracting that 5-dimensional vector or lower dimensional vector, which describes the image much better than the pixels could ever do, is really kind of what identifiability work is all about, recovering properties of the true generative process. And there's been a lot of work pre-deep learning. There was a Haverinen paper back in 1999, which proved a similar result to what we're going to discuss now. But this has been a long-standing goal of, if we have a data generating process and there's some underlying latent variables for that data generating process, can we recover them? What kind of objective can we use such that we can learn a function that inverts that data generating process and gives us back that 5-dimensional representation, which we can use for whatever task we want to use it for. When people say that identifiability is impossible, what they typically mean is the following. If we do likelihood maximization, and we get a statistical distribution over f of z, and let's say f of z is our deep network, which is mapping through the data generating process, mapping those ground truth latent variable to the inferred representation, the representation that we actually can use for downstream tasks. We learn a statistical distribution over that representation, which is entirely equivalent and indistinguishable from the statistical distribution over the ground truth latent variables, but does not actually capture the latent variables in a property that we care about, which could be disentanglement. And by disentanglement, what we mean is that we could learn a simple transformation between the ground truth variables and the representation in many different ways, but one which could be very useful is a permutation, meaning that if we have shape, scale, and position as these factors, we can ensure that our representation also has shape, scale, and position isolated in dimensions of its representation, and a single dimension of that representation is only has a non-zero partial derivative with respect to a single dimension of the ground truth latent vector. However, identifiability, impossibility proofs basically go about showing that you can construct for arbitrary data generating processes transformations for which the statistical distribution with respect to said transformation is the same as with the ground truth latent variable. However, a single dimension of that representation changes with respect to all dimensions of the ground truth latent variable, meaning you're the farthest thing from disentangled, you have a completely entangled representation. So there is a difficulty in general of kind of guaranteeing by just simple like IID, statistical maximum likelihood sort of distribution learning, that we can really capture these kind of disentangled variables, or in short, be able to recover like the exact ground truth latent variables and not just some entangled mixing of said ground truth latent variables. With that said, a number of works, like starting from 2016, have sort of shown that there's additional assumptions that you can make to get around an impossibility result and ensure that with an objective, I extract the ideal representation. With an objective, I extract a representation which corresponds with the ground truth variables of interest and is thereby ideal for any downstream task I may want to do in the future. And what we ended up doing in this collaboration with David Clinton, Lucas Schade, among other collaborators, is tried to find additional assumptions that we can make that correspond to practice. Because if we can prove identifiability, but we use an assumption that really isn't very practical, then that doesn't really characterize practice, and we can't really use it for experiments. And I think that overall we wanted to have useful sort of theory at the end of the day. And so the idea here was that we can take natural video data sets like YouTube and Kitty. We can kind of take segmentation masks and use that to decode some factors of variation, like X position, Y position, and scale. And we can track those factors of variation over time. And what we found is that irregardless of the factor variation we were looking at, and irregardless of the data set we were looking at, whether it was an autonomous driving data set or just YouTube videos, we saw the same kind of leptocritic, highly sparse, fairly Laplacian, not very Gaussian distribution, which essentially implies that factors of variation in video move slowly over time. And what we mean by that is that typically, if we look at an individual factor of variation and look at all frame changes, they don't really change in between frames, but when they do change, they could change a lot. And so then you end up getting a sparse distribution like this. And essentially, the way the identifiability result kind of comes about is that we, one, learn a generative model, which again, statistically matches the underlying data generating process in every sense of the word. But as in the impossibility proof, that's not enough. But what do we do in addition to that? We also make an assumption on the latent variables. If we assume that the data generating process, the temporal transition between latent variables, does correspond to, say, a Laplacian distribution or just a highly sparse distribution, which was a decent assumption given our data analysis, then we just enforce that our deep neural network, the generative model that we learned, also should have latent variables that also, when varying in time, have the same sort of characteristic. And if we both make an assumption on the probability distribution over observations needs to be the same, as well as the probability distribution over conditional latent variables needs to also be the same, we get around that impossibility result. And as long as the distribution isn't Gaussian, because Gaussian distributions are rotationally symmetric, a rotation is a linear transformation, and that's weaker than a permutation. And so with Gaussian distributions, that's kind of problematic for this kind of work. This isn't a Gaussian distribution, this is a Laplacian distribution and was found in nature. And because it's not a Gaussian distribution, and thereby rotationally asymmetric, we can actually get an identifiability result up to permutation using an assumption that was found by looking at natural video. But now, I guess maybe we were happy with the natural video assumption, but what we ended up not being that happy about was the generative modeling assumption, just because we want to have a methodology, a proposal that is appropriate regardless of the data that we kind of consider. When we consider high dimensional images, for example, learning a generative model is quite difficult. And if we look at common practice, that's not what's really being done. They're all variations on, say, contrastive learning or like more efficient ways of contrastive learning like BYOL or SimCM, but they all learn an encoder. They don't necessarily need to learn a decoder. They don't necessarily need to learn a distribution over the actual high dimensional observational variables. They just need to map the observations in a deterministic way to a lower dimensional representation and just define an objective that is useful for that. And so in a collaboration with Roland Zimmerman and Stefan Schneider, we looked at, can we obtain a similar results if we solely learn an encoder via contrastive learning? And the essential gist of this result is that if we actually look at that influencee objective and the details of it, basically, not just like in general what it is, but like how exactly it's instantiated, a number of assumptions are implicit in that objective, which really determine whether or not we can gain identifiability or not. And so what we mean by this is the following. If we look at the similarity metric that we're using, that has a whole host of assumptions that come with it, which is cosine similarity. Cosine similarity, L2 normalizes the representation and then uses a dot product to characterize similarity. If we L2 normalize the representation, we're living on a hypersphere. And if we use dot product to characterize similarity, then if we were to impose a probability distribution over the representation, the probability distribution over a representation that minimizes its objective function, if we were to look at that conditional distribution, it would also correspond to the same similarity metric, a dot product over a hypersphere, which is a very specific statistical distribution, a von Mises-Fisher distribution. And additionally, the fact that we kind of arbitrarily sample examples and then we just sum over them, we don't reweight or we weight all points really equally, and we just kind of sample IID, corresponds to a uniform distribution over our negative samples, that we all kind of points on the hypersphere are equally likely because we're not really controlling the sampling of the marginal distribution. We're very much controlling the sample of the conditional distribution or how we actually construct augmentations. We're not really making many assumptions at all about the discrepancies between the individual examples we may have in a batch. And so in terms of the theoretical results that we get, to give some intuition, it's again very much in the same lens as the previous work, where with additional assumptions, we can get these kinds of permutation or linear transformation results. But the way we get about it in this work is we show that if you kind of, by using a result from Wang and Isola, which kind of takes contrastive learning and decomposes it into an alignment objective and a uniformity objective, we find that we can recover this alignment and uniformity objective, which occurs in asymptotics when we have infinite negative samples, which is kind of typical of theory. We can recover that alignment objective and that uniformity objective if we minimize the cross entropy between a distribution over the ground truth latent variables and a probability distribution over the inferred latent variables or the representation that we actually extract. And if that the inferred distribution has a very particular form, and it comes from the contrastive loss, the influencee loss, and it is that von Mises-Fisher distribution that we were kind of talking about before, where we have this dot product being used as a similarity function for defining the probability distribution of an exponential family. And if the ground truth conditional distribution matches this in form, if it's also a von Mises-Fisher distribution that has a very similar form, you might imagine that like if we minimize cross entropy, we can set distributions equal to each other. And then since they have the same form, terms can cancel out, and then you can get a very simple sort of relationship between the representation and the ground truth variables. That's exactly how the theorems kind of went about. But I guess there were two concerns in terms of the next collaboration, which was with Julius von Kugelgen and Luigi Gresseli. With those previous works and really just identifiable representation learning and nonlinear ICA in general, in that the nice thing about Zimmerman et al. Relative to kind of Clint et al., which was the first work relative to the second work, is we move towards contrastive learning, which is more close to practice, but there's still two major problems with kind of the way we're sort of the assumptions that we were making in that setting, which still mismatch practice. Number one is the fact that all nonlinear ICA and disentanglement work assume that the latent variables are independent, and that just isn't true in reality. And that also wasn't true within like our identifiability work, the first identifiability work we did. For example, if we look at each of the factors individually, our assumptions make sense. That this sparse distribution over X position and Y position individually makes sense. But if we were to also look at this independence assumption that we were also making use of, it was kind of just sort of, it wasn't the focus of the work, because nearly every disentanglement method or nonlinear ICA method also makes the same independence assumption. That wasn't met at all in terms of these X positions and Y positions. We saw highly correlated variables. When X changes, Y changes. When X changes, area changes. And we can kind of think about as to why when a person is kind of moving in an autonomous driving video, as seen on the left, you also see that like they don't necessarily move in horizontal and vertical fashions. They typically move in diagonal fashions, at least with respect to, say, the 2D projection you're getting from the view. And as they move away from the camera, the area changes. And so movement corresponds to changes in almost all of these factors. So you'll see correlations. So that was something that we wanted to sort of not make that assumption, because we didn't find that that was true in practice. And that definitely relates with the causality literature, because that's also what causality is kind of looking for, that there are dependencies in nature and we want to capture them. The last thing, which is more specific towards our actual goal here, is that SimClear does not use positive pairs that correspond to, say, a von Mises-Fisher distribution or any kind of simple distribution over sort of a simple space in order to give rise to the positive pairs they use for alignment. Instead, with the idea that we want to kind of isolate the semantics and get rid of things like position and color, we're picking augmentations that are supposed to get rid of those variables. And so an augmentation like color distortion is supposed to get rid of color from the representation. And so color will change, but all the other latent variables do not change. So not only do we not want to make a specific distribution on like a specific assumption on what that distribution over positive pairs is, we additionally don't want to just generally make an assumption that all latent variables are changing across views, because the augmentations are specifically chosen not to do that. And what we end up finding, which we'll kind of get into in detail, is that if we start making assumptions which really correspond to what we do in practice, what we do in terms of SimClear, we get a theoretical result which also matches what the intuition was behind SimClear. And so if we want to formalize things, basically what we assume is that there can be causal dependencies and statistical dependencies within latent variables that don't kind of break this sort of invariance assumption that the augmentations give rise to. And how we kind of describe or characterize this invariance and variance is we kind of partition the latent vector into a content vector, which is invariant across the augmentation, and a style vector. So using color distortion as an example, as a data augmentation, color would be style according to a color distortion, but everything other than color, like position, rotation, object class, anything, would be content in this case. And that's how we would sort of partition the latent vector between content and style with respect to a given augmentation. And this may be different for different augmentations. And just like a note, because this will become relevant later on, obviously when we do data augmentations, we're not doing transformation over latent variables because we don't have access to latent variables. We're doing a transformation over observations. We could of course take a transformation over an observation, and then if we actually had access to the data generating process, go take the inverse of the function that maps the latent variables to the observations, really the data generating function, and get back the transformation in latent space that was the transformation in pixel space or observational space. And so as long as like technicalities, which do actually matter, are matched, we can still use a latent variable model to describe pixel level data augmentations. And so if we want to be formal about this, if content doesn't change, that would correspond to a Dirac delta conditional distribution. And if we want to also be flexible and allow for For one example, maybe color is style, but for another example, maybe position is style, meaning that different subsets of the latent variables can be style for different examples. We also kind of make an assumption and characterize the style distribution as such. And then also with regards to the whole making assumption about the specific form of the distribution, we don't make a specific form about the distribution of style variables. So all of this is very much corresponding with practice. And the final theorem is that if we sort of minimize a function, which we'll talk about how it corresponds to contrastive learning, we do isolate content. We do isolate what's invariant across the augmentations, which is exactly what was the point and what people have kind of the reason as to why we kind of decided those augmentations in the first place. That according to the contrastive learning objective, we should only be recovering the information as invariant across the augmentation, and we design very good augmentations. The only feature of the observation that is invariant across the augmentations is what we care about for downstream tasks, which is the class variable, for example. And just for a quick aside on the technicality, the one aspect here which may be kind of unclear, so this looks very similar to kind of the attraction that we looked at in the influence E, but what is this? This is differential entropy. And essentially the idea here is, again, with that Wang and Isola paper, repulsion, the way we kind of enforce we're not going to collapse, in contrastive learning corresponds to enforcing a uniform distribution over your latent variables. The uniform distribution is the maximum entropy distribution in many different spaces, and an entropy maximization corresponds to preserving information or non-invertibility, again, coming full circle to the reason as to why we do contrastive learning in the first place, which is to prevent collapse. And that way we can kind of ensure that we don't collapse, basically. And that's kind of how we would mathematically characterize that we don't collapse through this kind of entropy maximization. So in terms of experiments, we did see something additionally interesting. So one thing about the theory is, yes, the contribution kind of bridged theory and practice in a sense. But what was maybe not that attractive about the theory is it didn't give rise to something surprising, which could have maybe indicated that we're doing something suboptimal in terms of contrastive learning, and we could be doing something better later on, and therefore provide a prescription for later research. We didn't really get that through our very descriptive theory that we had, but we do have hints at that through our experimental analysis. So for our experimental analysis, we just tried to, again, in order to do a controlled study, we sort of need to have the gradually latent variables, which means we need to have synthetic data generating processes. But we tried to be as complex as possible, which is why we kind of took a bunch of latent variables and took a bunch of knobs in Blender, which is a pretty highly complex renderer, and rendered observations. So we could have, we're not like specified to numerical simulations. We can use renderings that are highly complex while also still doing our identifiability analysis. And then in line with kind of our differentiations between this work and previous work, we imposed a causal graph over the latent variables as opposed to assuming they're independent. And we did not assume like some kind of latent transformation was being used for contrastive learning. We actually use the data augmentations. What we did is we compared those data augmentations to their corresponding latent transformations. And while there's a lot going on in this figure, all I want to say about this is overall, latent transformations and data augmentations that are similar, that target similar variables. So color distortion is targeting similar variables as actively going in and changing the hue latent variables and then generating another example, which is something we can't do in practice, but is something we can do with a controlled study. They do behave similarly, but there are differences. And in a sense, for what we really care about, which is kind of decoding the semantics, decoding the class variable, we get that in terms of latent transformations, but we only get that if we eliminate shortcuts with data augmentation. So what I mean by that is the following. Data augmentation individually, individual color distortion, individual crops, that should isolate, that should still like characterize object class as content, and we should still be able to decode content from the representation and therefore get a high R-squared score. But we can't if we do an augmentation isolation, but we can if we do a latent transformation in isolation. And so as an example, we couldn't in terms of data augmentation here, but we could in terms of latent transformation. But we can in terms of data augmentation if we do both crops and color distortion. And that's just really a matter of what crops and color distortion influence. They influence different things. They eliminate shortcuts. So crops make position and rotation style. Color makes hue style. And while we do see high R-squared scores on position and rotation, this is honestly a consequence of the fact that we had a causal graph where object class did causally sort of influence the object position, object rotation. So there's a correlation there. But regardless, we are definitely making those style because we cannot, if we look at any of these two pairs, they're 100% changing. So the only thing which is kind of content when we do crop and color distortion is class. And so we're seeing some kind of shortcut learning. We use data augmentations, but we don't get that shortcut learning if we're doing latent transformations. But what are latent transformations? I think we can kind of get an idea at it if we sort of look at rotation. So a data augmentation rotation will be an image level rotation, where you literally take all of the information corresponding to the image and rotated it. But a latent transformation of changing rotations will be changing the object rotation, which will be really going into the scene and moving and actually rotating the object and then taking a picture of it, which is something we can't do with data augmentations, but it's something that we can do in the real world. We can do so with interventions, interactions, or just passively observing transitions, because objects rotate and move and transition all the time. And so leveraging video has been kind of I've explored it in my own recent work. It's been explored in many different recent works. It's difficult, and I would say it's difficult because of a controllability aspect. In video, you're passively observing the video. You can't do the same thing as with data augmentations, that with any one of your images, you can get a huge amount of variation because you can just impose your data augmentation on any image indiscriminately. No, for video, you have to hope that your video sequence is going to show variation. You're not going to see the same kind of variation for every single kind of image because that's just not how video is. We're just taking video basically. But if we had control, we could do that. And we do have control on robotic setups. And there's been some work to explore, like we can actually change things there. But then we have an issue of complexity that we can't really do robotic setups with also like the natural image complexity, or less. Also, it's kind of hard. And so maybe a suggestion for fundamental research is to look at controllable generative modeling, where you're sort of the more progress we make with that, and you can see examples of this with like DALL-E and Stable Diffusion and things like that, with these kinds of huge generative models for which the text prompt gives you some kind of control, we could possibly move past augmentations by using that in order to kind of condition on an existing image and get lots of different variations that we sort of control for. So we can kind of create a color distortion, we can create a crop, or we could create a object, we could create whatever we want, and we're not restricted to having to operate the image level because we're conditioning the generative model on what we want. And the final thing that I'll say is that in medical applications, you do have an additional tool for moving beyond data augmentations, which is the fact that you can use any information that you have in the medical application to come up with a better approach than what fundamental research is able to give you. And I think this has already been exploited. So Azizi et al. Has looked at, say, how self-supervised learning transfers better than supervised learning. And what they found was that, well, pathology is something that we often have. In a sense, patient metadata is something that we have. And that patient metadata is something that we may have for different medical images. And that patient metadata can be used to kind of decide what are two related images. And so one thing that you might get out of patient metadata is pathology. And so you could basically then just take views as not augmentations, but just different images with the same pathology. And then that's what you're going to, the invariance between those images is what you're going to recover by contrastive learning, as was proven previously. And that what's exactly the same across these images is the pathology. And the pathology is what's very much related to any downstream task you might want to do with medical images in terms of, say, decoding the medical condition. And so, in a sense, leveraging patient metadata, which gives hints or is kind of a biomarker for the medical conditions that we may care about downstream, and using that to form pairs, if you have access to the data, is something you can do if you kind of focus in a medical application setting, and something I would suggest further work can kind of explore. Thank you.